Today we're going to talk about a few things, and one of them is logistic regression. We've only talked about dummy classifier and decision tree classifier so far. This is going to be a new classifier. And the motivating example for introducing this new classifier, the data set of the week, in fact, is going to be a movie review data set. So as I mentioned, we're going to have a data set every week. Last week was the cilantro, which didn't turn out so great. This time we're using a real data set of IMDb movie reviews. And so each review is going to have a label of either positive or negative. And we're going to try to predict the sentiment based on the words in the review. So if the first review is this movie was excellent, the performances were Oscar worthy, can we maybe automatically detect the presence of the word excellent and classify this as positive? What a boring movie, can we automatically detect, not by pre-programming that excellent is a good word and pre-programming that boring is a bad word, but by learning that from the data set using supervised learning. That's going to be our task. And so logistic regression is something called a linear classifier. And what it's going to do is we're going to associate a coefficient, which is just a number, positive or negative number, with each word, which is basically saying how positive that word is. So maybe you'll learn excellent is a positive 1.93, disappointment is negative 2.2. We're going to try to automatically learn these coefficients from the data. Again, not programming them in by hand, but by learning them from the data, because we have labeled data saying if the reviews are positive or negative. And then when we're given a new review that we want to classify, it got a bit boring at times, but the direction was excellent, acting was flawless. We're going to pick out these keywords, and we're going to just add up the coefficients corresponding to those words. That's it. So for example, the coefficient for boring is negative 1.4. The coefficient for excellent is 1.93. The coefficient of flawless is 1.43. We're just going to straight up add those numbers together. And then when we're done, we're going to look at the sum. And if it's positive, we're going to predict positive movie review. And if it's negative, we're going to predict negative movie review. And that's going to be how it's going to work. And so, well, we're going to get to this in a second, but basically we're going to make a data set where the columns or the features are the different words, and then we're going to have one coefficient, also called a weight, per feature, and so that's going to be per word, and we'll just leave this bias or intercept thing for the moment. Okay, I guess. Okay. I was going to say this feels like I should stop for questions, but hey, I put one in very soon, so perfect. Okay, so we're going to talk about a few of these aspects of scikit-learn logistic regression today. So now we are at a designated question period, and now the confusing part is that I don't really know which questions have already been answered, and that's kind of what I was worried about. So let me try to scan through here. So there's a question about cross-validation, and I guess I'll just recommend using lots of folds unless it gets too slow. Yeah, so someone says, hey, this is still a positive review. Right, okay, yeah, that sounds fine. It's still a positive review. Why do we call it a linear method? That's actually not such a simple question. Kind of like linear regression. We can just say it's because we're adding these scores together. It's a little more complicated than that, and it's about it being linear in the coefficients. I don't really want to go into too much in this course. But there's definitely plenty of discussion about that in 340. How will the weight deal with not? Yeah, great question. So this is not going to be perfect, because if it says it was not at all boring, then this is going to be messed up. So we're going to talk about that later in the course when we get more into text in the second half of the course. For now, that's just going to be a problem that we're going to ignore. How would we detect sarcasm? Yeah, so all that kind of stuff we're going to leave to another lecture later in the course about text. And we're just going to do it very simple for now. Would it produce a probability? Absolutely. We're going to talk about that later today. That's what this predict proba thing is. We'll get to that in a bit. Okay, now we're going to really get into the real meat of today's class. CountVectorizer and this thing called the golden rule that is a very subtle and important part of the course. So I have downloaded this data set. You should be able to download it as well. And yeah, I did not push it to the repo because it's large and I don't have permission to redistribute it. So you can get, it's very tempting for, I just need to stop looking at the chat. Right, okay. So I load in the data set. I do some pre-processing that we're not going to worry about. And I just take a subsample of 1/5 of the rows. Otherwise, the code will just run really slow if I have the whole data set is quite big. So even with 1/5 of the data set, I already have 10,000 movie reviews. And yeah, basically we just care about the review column with the text and the label column with positive or negative, and they've pre-decided which ones are train or test. We're just going to ignore that. So yeah, 10,000 rows, 4 columns. And so the input is basically the text of the review. And what we're used to is this tabular data set thing where you have a bunch of features. Column 1 is a feature, column 2 is a feature, like we saw before. So you saw that in the Spotify thing, in the homework, the cilantro. But this is just a bunch of text. So the thing we really need to focus on for the next 20, 30 minutes is how do we turn text into a bunch of columns? Because that's how the format we're used to. And the answer is going to be each column is going to correspond to a word, and we're just going to look for the presence of that word in the review. So here we have a new scikit-learn object, CountVectorizer. And I'm going to make a new CountVectorizer object. And this is a new type of thing in scikit-learn that we have seen before, because it is not a classifier. It does not have fit and predict. It's a transformer. It is used for pre-processing data. It's not a classifier. And we'll talk about how it works in a second. So I'm just going to set binary equals true for now. That just says we're only interested in does the review contain the word or not. By default, it counts how many times the word appeared in the review, and that's fine too. But just for simplicity for now, or for teaching purposes, we're just going to check if it's present or absent. So this transformer, this vectorizer object, still has a fit function. And what fit does is it's just going to look at all the reviews, and it's going to see what words there are, and then it's going to decide, depending on the parameters you put in here, which words does it actually care about that are going to be sort of the keywords. And we'll talk about that a bit more in a second. So I'm calling fit, but now there's no predict, there's no score, but instead there's transform. And so what transform is going to do is it's basically going to turn all those rows of text into rows of whether the word is present or absent. So I'm going to call transform. And now if I just look at the first row here, it's basically, well, here it just looks like a bunch of zeros. But let's look, so this is one row. This is one movie review. And this is the shape of the whole thing. So we had 10,000 movie reviews, remember? And we've created 53,000 columns. Which is a crazy amount of columns. So we have 53,000 features now. And where that came from is that it just took every single word present across all the reviews and it said, I'm going to make a column out of that. And so you can actually see what the words are. And I mean, here are the first 20 words, and it's just taking anything between spaces and calling it a word, basically. So these are a lot of kind of ridiculous things that we wouldn't really consider words. And so we can get rid of this by using some of the hyperparameters of CountVectorizer. Okay, and yeah, we'll talk about this more later in the course when we get more into this. So here's what I'm doing. Min df equals 50 means a word has to appear at least 50 times in the entire data set in order for us to consider it. So if something just appears in one review, that's not good enough. It has to appear 50 times. That's what min df, min document frequency equals 50. And so just like a classifier, I put in the hyperparameters when I make it. And I still call fit, but I'm now calling transform instead of predict. And when I do it this way, instead of having 53,000 columns, I have 3,000 columns. So because there's only 3,000 words that appear that many times. And so that's good. That's more manageable. You can also, there's other hyperparameters here. So I can just say, hey, I only want the 1,000 most popular words in the data set. And I can do the same thing. Oh, just a note here that there's a shorthand called fit underscore transform, because you'll notice I keep fitting and then transforming immediately after. So if you want, there's this shorthand fit underscore transform. It just does both in one line of code. That's all it does. So now if I say I only want the 1,000 most popular words, then I get this, again, 10,000 movie reviews. Each one used to be a bunch of text, but now it's 1,000 columns, and in each entry there we have ones and zeros saying, does word number 7 appear in review number 9? If so, put a 1 there. If not, put a 0 there. And so it looks kind of like this. Review 0 contains the word about, contains the word act, contains the word year, but does not contain the word years or yes or yet or York. Review number 9999 contains 10 about across, but it does not contain any of these other words, and that's why there's zeros here. So now we have this table format that we were used to from last week, a numerical table. Rows are examples, columns are features, we have numbers inside, and now we can immediately throw this into decision tree classifier. And so CountVectorizer has gotten us from this unfamiliar format of text to this familiar format of a numerical table. Okay, and the y is just positive or negative. Okay, Q&A. So, and also I think it'd be nice to have space here. Okay. Are there any questions, Yushi, that are still outstanding, or have you answered all of them?
Yeah, so I was trying to keep the thread of all the questions, and so far so good.
Okay, any further questions before we move on?
Yes, I have a question. Can you guys hear me?
Yep, go for it.
Cool.
Just a warning that your voice will be on the recording, but if you don't mind,
well,
go ahead.
It's already there. So basically, I'm not quite sure I understand the reason why we have to see the same word 50 times before we consider it.
Okay, good question. So if a word only appears once, it's probably not going to be that useful for prediction, because the chance that it'll show up in a new review is very low. Furthermore, and probably more importantly, if a word only appears once, we just have so little information to say, is this word positive or negative? Because we have 10,000 reviews. We have one review, it was positive, it had that word in it, but it also had a bunch of other words in it. So we really don't have enough information to say that word should have a positive coefficient or a negative coefficient. And so it's kind of like we want a minimum amount of data about a given word to even feel a bare minimum of confidence that we know anything about that word. So if a word appears in 50 different reviews, then we can say, well, if 49 of those reviews are positive, sure, there's other factors because there's other words, but we have more data about that word. And so that's kind of the basic idea. As we're going to see later, the problem with keeping things in that we don't have a lot of data about them is they actually lead to overfitting. And that's something we're going to explore over the next few weeks, kind of slowly build that intuition about why it would lead to overfitting.
Okay, thank you so much. And I guess a follow-up question, because I kind of lost track of your teaching after I got lost on the 50. What is the reason why? How does it choose whether it's a 0 or 1?
So a 1 means that word is present in that review.
Okay.
So the word about is present in this first review. The word across is present in this last review, and the 0 means that word is not present in that review.
Excellent. Thank you so much.
Sure. Yeah. So basically, we're just turning text into a row of numbers using CountVectorizer because we need numbers to be able to use our classifiers. There's another raised hand. Go ahead.
I have a question. Is there a way to get rid of certain words that you know will pop up a lot, like about, able to, or like years?
Yeah. So those are called stop words. You can get rid of, you can exclude words. There's a lot of options here that I'm glossing over, but we will come back to that later in the course. Absolutely.
All right, thank you.
Yes, the numbers on the left are just the row number. That's just the index that Pandas puts in by default. Okay, let's move on. Be curious to hear what you all think of this format, but I'm liking it so far. Okay, so now we're going to split the data. And so just to note that there's two different syntaxes for calling train test split. I think this is the one we were using so far, where you pass in a data frame and it gives you train and test. Again, it's randomly splitting the rows. You can also pass in, if you've already separated off your features from your targets, your X from your Y, you can also pass it in this way. And then it'll return the 4 things in an order that I find very unintuitive. I keep expecting it to be X train, Y train, X test, Y test. So just be careful to note the order that it passes back the results. I actually messed this up earlier today and I was trying to debug it. Yeah, okay. Train test split is a standard method from scikit-learn, not from Pandas, but yes, it's imported at the very top of the notebook. And I'm going to keep trying to ignore the chat. Maybe I should minimize it. Okay, so let's keep going. So I'm going to call train test split. I've already separated off the X and the Y. To remind you, the Y is just positive and negative, and the X came from the CountVectorizer. The X is basically this. So I'm going to call train test split, and I'm going to ask you, are we all good here? Did I do anything sketchy? So the answer is that we're not all good here. I did do something sketchy, and it's a rather subtle point. So let's digest it together slowly. Remember that the test data is supposed to be unseen data. The test data should be something completely fresh, and you want to see how well you do on completely fresh data, because that's what's going to happen in deployment. You're going to get new things that you haven't seen before, and you're going to have to try to predict the answer. But here, there was a contamination or a leakage or whatever you want to call it, that the test data influenced how we pre-process the training data, because we fit that CountVectorizer on the entire data set of all the reviews. So we, for example, use the test data when determining what were the most frequent words, or did a word occur this many times. We were looking at the entire data set, which include the test data. In fact, there may be some words that appeared 50 times in the test data and don't even appear in the training set at all. And those words might have made it in, but they shouldn't have made it in because you're not supposed to see the test set. And so it's like cover your eyes. Like we've seen things that we weren't supposed to see because we're not supposed to look at the test set. We're only supposed to score on it at the very end as unseen data. And so if we cheat like this, then our test score is going to be too high in a kind of nebulous, hard to quantify way, generally speaking. But we want the test set score or error to be as accurate as possible a measurement. The test error is like the thing you want to go to your boss with and say, hey, this thing's going to get 90% accuracy. And if you say it's going to get 90% accuracy and then the boss says, okay, that's so good, let's do it. They spend $300,000 on it and then it only gets 70% accuracy, they're going to be mad. And so you really want your test score to try to reflect how well you do on unseen data. And so you need to be careful about this contamination. And so we're calling this the golden rule of machine learning, that the test data should not influence the training process in any way, which is another way of saying the test data needs to be unseen data. And we need to make sure not to violate this. But it sounds obvious, but there's so many ways to violate this rule in unexpected ways. And so we're going to see that more on Thursday with cross-validation. There's even more ways to make this mistake accidentally. Okay, so the golden rule. Yeah, I think we already talked about most of this. Basically, the test set should only be used once. Let's not worry about this for a minute, but let's go here. So even if you only use the test set once, it's not going to be a perfect representation or estimate of deployment error. Again, remember, deployment is when you actually use the thing in this hypothetical situation. You will never actually, the deployment score is how well is this going to do when we put this into production and actually use it. And the test score is kind of a stand-in for that. So of course there could be bad luck, and the smaller your data set is, the more luck there is involved. It could be that the deployment data is actually different. So it's, I don't know, it's only on modern movies, and so all of what we did is kind of wrong because it includes old movies. There's all those kinds of changes that can make the generalization worse. But yeah, we don't want to add yet another source of error, which is that we contaminated and basically indirectly looked at our test data by allowing information from it to leak into our training process. So that's what this golden rule stuff is about, and we're going to be coming back to this several times. And I didn't have a Q&A here, but I think it's important because we just introduced an important concept. Are there any questions about this golden rule stuff?
Yes, I was just wondering if the test data set is just being used sort of as a buffer before you actually deploy for your final sort of to see how well your model does on something that's completely like the deployment prediction stuff. It's not really within the data set that we already have.
Exactly.
Yeah, okay.
That's exactly. The deployment thing, we don't have the data yet. It's kind of just in our mind. The test is like, we do have it in our data. And yeah, the workflow we're going to go with in this course is exactly what you said. Save it to the end and just use it to make sure we're doing how well we think we're doing. Yeah. Okay, so we messed something up, apparently, because we looked at all the word counts and all the words and all the reviews, and so we don't want to do that. And so what we should do generally is we should split right away. So I'm going to load the data set, just do that same pre-processing as before. We can ignore that. And I'm just going to immediately, first thing I'm going to do, no funny business, I'm splitting. If I don't touch IMDb test while I'm pre-processing my train, there can't possibly be this leakage. And so that's great. I'm going to do that. I'm going to just split off my X and Y. I'm going to make my CountVectorizer. I'm going to transform X. I'm going to, give it away. I'm going to transform Y, transform train, transform test, and now surely we're all good, right? And I accidentally scrolled down and you already saw the no. So this seems legit because I split it off right away. And I did my train thing on my train. I did my test thing on my test. But we're actually not all good, right? And there was actually a different problem here that is not a golden rule problem. And so let me talk about that. Okay. If there's a question saying, what does transform do? Transform converts the text into the row of ones and zeros. I'm really going to have to get more disciplined about. Okay. Okay, so here's what I'm going to do. I'm going to make a decision tree. I'm going to fit on X and Y train. That's fine. And I'm going to try to make a prediction on X test. So this should all be fine, predict or score or whatever. And what happens here is I actually get a Python error. And the Python error is coming from somewhere inside of scikit-learn. And it's saying, hey, the model is expecting 2,500 features, meaning that's what you told it when you trained it, but now you're giving me 1,000 features, and that doesn't make sense because it has to be the same number of features. So is that really true? Well, yes, right. So is that really true? Yes, we have 2,500 columns in our training data and 1,000 columns in our test data. And as you know, that doesn't make any sense because the train and test is a split of rows, right? You have your data frame and you say, these rows are my test, I'm going to take them away, and everything else is for train. And so, yeah, we had used 75% of it for train, we used 25% of it for test, but something got messed up and they have different numbers of columns. And the reason for that, let me scroll up, is that is right here. So this is fine. I said the vectorizer should look at the reviews in the training set, and it should say, what are the words? And then I'm going to make each column corresponding to a word, and I'm going to check if each word is in the review or not, and put a 1 or a 0 there. But here, on the test side, I'm calling fit transform again. And so it's again looking and saying, hey, what are the words in the test data? But that's not, the columns in the training set and the test set have to have the same interpretation. Because, for example, if you have a decision tree and it's trying to say, is the word excellent there? If so, predict positive. And the word excellent is column number 5. It had better be column number 5 in the test set as well. Otherwise, everything's just going to be all jumbled and not make any sense. So what's happened here is that we have this mapping from words to columns. Column 1 is excellent, column 2 is about, column 3 is tree. And that mapping needs to stay consistent between the train and test set. Otherwise, it's all just kind of garbled nonsense when we try to make predictions on the test set. So that's what happened here. It's not a golden rule issue. It's a pre-processing issue. It's a different type of mistake we made. And thankfully, I'm so happy Python threw an error because when Python throws an error, that's doing us a big favor because we know there's a problem. The golden rule thing is much more scary because Python did not throw an error and we just contaminated our test train split and no one's actually telling us we did anything wrong. So yeah, you're lucky when you get a Python error, but you don't always for all the problems that can happen in supervised learning. So that's why we have to be so vigilant and so careful. And in fact, to make matters worse, if we had set, so the only reason we got an error is because it said there's a different number of columns in the train and test set, which doesn't make any sense. There has to be the same number of columns. But imagine if you used max features equals 1,000, which is telling it, hey, I want 1,000 columns, then this would not have thrown an error. And we could have done it and everything would have been fine. But the results would just be complete garbage because, again, because we're fitting the vectorizer on the test set again. And so let me illustrate this for you. After we make the vectorizer fit on the training set, here's the first 3 columns. The first column corresponds to 10, the second column corresponds to 20, third one corresponds to 80. And when we do it on the test set, so apparently the 30 just didn't show up in the training set or the 80 just didn't show up in the test set just by the randomness of the splitting. And so now the columns are corresponding to different things, which is a disaster when you're actually trying to learn a machine learning model because if the decision tree learned that 80 is a good thing, it's going to look at that third column, but the third column doesn't correspond to 80 anymore in the test set. So this is even worse because we're not getting that Python error because each one has 1,000 columns and the results are just completely wrong. So how do we fix this problem? And yet this time I'm not going to say, just kidding, this is all wrong. This will be the correct version. So we're going to start by train test splitting because we want to do that right away. We don't want this contamination golden rule issue. I'm going to make my CountVectorizer. We already talked about that. And here's the thing. I'm going to do fit transform on the train before. But the thing that messes it all up is I never want to fit the vectorizer in the test set because that's saying decide which columns are which based on the test set. But no, I want to decide which columns are which based on the training set so that the columns have the same meaning in both cases. And so here I'm only calling transform. I'm not calling fit transform. And that's the whole difference to solve the problem. I'm saying take the vectorizer. It's already been fit on the training set, meaning it's already decided which column corresponds to which word depending on the training set. Use that same mapping of words to columns on the test set. Just transform it. Don't refit. Don't relearn the mapping of words to columns. And now everything's okay. And now we're not going to get any errors. And we can get some actual scores. And we can see we have this overfit decision tree. Okay, that was some pretty serious business. So let's take some questions. In the case that a word is present multiple times, would that have more than one column? No. It's just one column for a word. What's happening, and let me scroll up a bunch. Sorry for the scrolling. Because we set binary equals true, it's just ones and zeros. If we didn't set binary equals true, you could have a 2 here or a 3 here, which is saying the word act appeared 3 times in review 0 or something like that. Looks like the next one already got answered. Are there any other questions? For 50, okay, let me scroll down.
All right, is it more useful to have the binary state or more useful for the numerical state? Because right now you put the binary as true, false. So sometimes you want to see the number of occurrences happen for the particular column.
Yeah, you can decide based on what you're doing. I mean, I'd probably use the actual count most of the time, but I just wanted to go with this really clean explanation at the very beginning that you just take the coefficient for the word and you add up all the coefficients for the words in the review. It's not that complicated if you just have a 1 or a 2. It's just like if the word appears twice, you multiply the coefficient by 2 and add that in. But it was just a bit easier to explain this way. So that's why I'm doing it this way. Okay, I'm very confused about fit here. The vectorizer is not a predictor, then why are we calling fit? Okay, right. So the vectorizer is not a classifier, but it still has 2 stages. So this is an excellent question. So stage 1 is fit. And what fit does is it looks at all the reviews and counts up how many times each word appears, throws away all the words that it doesn't like because they appear too few times or whatever other restrictions you puts in, and then creates a mapping of the first column is going to be, I got to scroll up again, really sorry, I know scrolling is a bit dizzying. It creates this mapping when you call fit. The first column is going to correspond to 10, then 20, then 30, then 80, then able, then about, then above. And on any word that doesn't appear here, it just got thrown away. That's what happens during fit. It makes those decisions. Transform actually produces this arrays of ones and zeros. So it transforms text. It looks at the mapping and it says, okay, well, for this review, there's not this word, not this word, not this word, not this word. There is this word. And so transform actually creates this tables of zeros and ones. And so when you fit on train, it makes this mapping. It now decides what the columns are going to be. Then you transform on train, you get these zeros and ones. And then when you transform on test, you get this zeros and ones for the 2,500 test reviews, but it keeps the column mapping the same. Whereas if you refit on test, it might have decided that actually able was going to be the first column, and then there would be this misalignment between train and test. I see a raised hand. Go ahead.
A quick question. I was wondering if you can explain a little bit about the coefficient. So we saw like the coefficient for excellent is about 2, and for boring was about minus something. Is there any like hyperparameter that you can choose to like put some limits on the coefficient?
Yes, we will talk about that. That's coming later today. We'll talk more about the coefficients. Okay, another raised hand. Go ahead.
Yeah, I'm just inquiring about how fit works. Is it almost like a decision tree? So if more than 50% is positive, then it...
For logistic regression, you mean?
Yeah.
We're not going to talk about that in this course. I'm going to have to defer that to 340. Yeah. Which you can take next term with me if you want. Yushi, is there anything else in the chat that needs to be addressed?
Yeah, I'm trying to keep the thread and answer them.
You think it's fine?
Yeah, it's fine.
Okay. It's 11:48, so let's take our 5-minute break and resume at 11:53, and I'll hang around in the meantime in case there are more questions. So see you in 5 minutes. Okay, recording is back on. And onward we go to answer some of the questions that came up earlier about the coefficients and probabilities. This is your chance. So back to logistic regression, which we talked about at the very beginning. I'm going to make a logistic regression object. Again, there's hyperparameters just like there is for decision tree. This max iter is not a hyperparameter I really want you to worry about. It's just they changed some defaults in scikit-learn version recently, and if I don't set this, it'll give us a warning, and I just don't really want to see the warning, so I'm setting this. But you can ignore this max iter thing. So I'm creating a logistic regression object. I'm fitting it. And by the way, I'm not going to do any cross-validation today. I'll return to that next class. And the reason for that will become clear next class. So I'm just going to live only in my train and test world for today. Because there's one more thing we need to cover before we can go back to cross-validation. Okay, so I'm going to train on my train. I'm going to get my training score. And I'm going to get my test score. And one thing that's nice is our overfitted decision tree that we didn't really tune was super overfitted and didn't get a very good test score. And our logistic regression did better. So I'm actually violating my own, I should really, okay, I got to import it. And a waste of time, but on the other hand, it's important to show good habits if I'm gonna need to practice what I preach. Okay, so our dummy classifier is getting 50%. So yeah, that basically means we have a balanced data set, like half are positive reviews, half are negative reviews. And so logistic regression is getting 80-something%, which is cool. But what I want to talk about now is predicting probabilities, which someone asked about earlier. So logistic regression does fairly well. It has these coefficients we're going to explore in a minute, but also it has this new and useful method, predict proba. So predict returns the class with the highest probability. And so you could think of predict proba as actually like the real output, and predict is giving us kind of a summary of that by just looking at the probabilities and saying which one's the highest. And so here's what we can do. We can call predict proba on our test data here, and this is the result. So it is a 2500 by 2 array, 2500 because we have 2500 test examples, and 2 because giving us the probability of each class. So probability of it being I just have to do that to check the order. Okay, the first column is negative and the second column is positive. So the probability that it's a negative review here is, I guess, 2% or 3%, and the probability of there being a positive review according to this thing is 97%. These things are a bit hard to read because of the scientific notation. 2.4 times 10 to the negative 1 is 0.2, so it's like 20% negative, 70-something% positive. So yeah, that's what predict proba gives us. Instead of just giving us a prediction for each review, pos, neg, it gives us probabilities that add up to 1. And so since they add up to 1, we only really care about one of them. So I'll just grab the second column. This is the probability that it thinks it's a positive review. The reason why it gives you both, even though they add up to 1, is if you have like 5 different categories that you're classifying, then it'll show you all the probabilities. So yeah, we'll just not worry about that for now. Okay, so here's the probability according to logistic regression that the thing is positive. And so what's really useful about that is it's kind of telling us how strongly do you feel that this is a positive review? How strongly do you feel that this is a negative review? And where this is coming from, as I told you before, it's adding up the coefficients corresponding to the words. And basically, if that sum is really big, then it's going to have a really high probability. And if that sum is like really negative and big, it's going to have think it's very negative and have a probability close to 0. So what's kind of cool is that we can actually look at all of these probabilities. We can take the maximum of them. So here it's 99.99999% confident that this is a positive review. I should stress, and I'll say this again, just because logistic regression gives you this probability doesn't mean you should go to your boss and say, I, a human, am 99.9999999% positive about this, because this is just a mathematical construct, and as I'll show you later, you can change hyperparameters and get different probabilities. And so this is not for you to believe that that is the probability, but it's just a score. I would rather you just think about it as a score between 0 and 1, a confidence score between 0 and 1, and not really think of it as a probability, because I mean, yeah. I don't even want to. You can take a statistics class and they'll talk about logistic regression, and you can learn more about under what circumstances it would be reasonable to call this a probability, but I would rather just think of it as a score. So let's find that review that it's so confident about. Review number 1594. So here's the review. I guess what I'm seeing here, I'm not going to read this right now, but what I'm seeing here is that it's long, and that's probably why it got such a high score, because there's just a lot of words in this review. And so it had a lot of chances to get a high score. We can also find the most negative review. And again, it's long, and I'm pretty sure this is a negative review. And so that's funny. And I think the probability here is probably extremely close to 0. Yeah, so it's 99.99999 sure it's negative, or in other words, 10 to the minus 13 chance that it's positive. Okay, right, so questions.
Hi, sorry.
Oh, go ahead.
Oh, sorry. My bad. I didn't know you were going to read off the chat.
Okay, yeah, let me just take a quick look at the chat here during this question period. Yeah, so what is it? There's one question I don't fully understand, so I'm going to skip that for now. Is a 70% score good? It completely depends. As I said, there's this best error that we talked about last time, so it's very hard to answer this question, but it is good to start with dummy classifier, because if dummy classifier gets 90%, then 90% is horrible. And so I would at least start with that to get a sense of what's good, but it's a very hard question to answer. Is there a way to see what words? Yes, that is exactly the next thing we're going to talk about. So hold on tight for that. How does it translate values from adding coefficients to a percent? Yeah. I would say that take that in 340, but it's really not that complicated. So if you remind me on Piazza after, I can put it in here. It's basically like an S-shaped function that maps numbers between minus infinity to go between 0 and 1. So yeah, there's some mathematical function that maps a number to the score between 0 and 1. Yeah, if the probabilities are exactly 50-50, I don't know. The people who made scikit-learn had to decide about that. Either it may predict randomly or it may be hard-coded into scikit-learn. I don't know, but you can try it out. So from logistic regression, where did it define the coefficients? Yeah, great question. So when you called fit, these coefficients got created. So it looked at all that table of zeros and ones, it looked at the correct answer, and from that data, it learned which words are positive and which words are negative, and we're about to look at those coefficients. That's the next thing we're going to do. But yeah, that all happens during fit. And then during predict or score, it uses those coefficients to give you these scores. Okay, so here we go. One thing that's awesome about logistic regression is these coefficients, where we talked about the words. And so the way you get this out of the logistic regression object is by the coef underscore attribute in scikit-learn. So here are the coefficients. And this is a bit meaningless to us because we don't know which words they correspond to. So the way you deal with this is you can see what the words are using this get feature names in scikit-learn. So here's the first, I don't want to look at this many. Here's a bunch of words, here's a bunch of coefficients. And so if we put them in a data frame, we can actually look at it. So yeah, by these pandas data frames, like they're useful for actual data manipulation, but they're also just so nice for printing things out nicely in Jupyter. It's awesome. So I just put those in the data frame to print them out nicely. So here you can start to see the coefficients. So 0, 0, 0 has this coefficient. By the way, I'll use weight and coefficient interchangeably. Sorry about that. That's like the statistics machine learning issue. So now you can start to see. And what's nice is if I sort them, because if I sort them, then you can see the most positive at the top and the most negative at the bottom, just because pandas prints out by default the first 5 and the last 5 when you print out a data frame. And so this is awesome because we can see it's actually learning. And again, no one told it by hand that perfect is a positive word. It just noticed when you called fit that a lot of reviews with the word perfect in it had the thumbs up label in the Y where you gave it the right answer. And so it learned this. And yes, someone's pointing out there could be issues with this, but I think this is pretty cool as like a first pass, and we'll go into more detail later in the course. So yeah, pretty awesome to see this. So we can explore one of our test cases. So for example, test example number 5. So apparently for this one, it's 99.9% sure this is a positive review. Again, the score is 0.999. Let me put it that way. It's a heavily towards positive. So just to clarify, by the way, that means if we call predict, it's going to give us a 1 because that probability is more than 0.5. Yeah, okay, it's going to give us a positive. So here's the review. And we can look at which words are in the review. So there's 94 keywords in this review. And long story short, here's the data frame of length 94 with all the words in this particular review that we're looking at, test example number 5. So these are the 94 words in that review that were part of the bigger list of keywords. And here's the weights for all of those words in that review. And if we sum that up, then we get this positive number, which is why it's predicting positive and why the score was close to 1. And the bigger this number was, the higher that score would be. So what's so cool about this is when it makes a prediction, we can dig into it and be like, hey, you logistic regression, why did you make that prediction? And you can inspect the coefficients and you can inspect the words in that review and look at, oh, why did it make that prediction? Well, because these were the words it picked up and these were the weights it learned for each word, and it added those all together, and that's why it did what it did. So this is something called interpretability in machine learning. It's the ability to understand why it did what it did. And it's a really important theme in machine learning that we'll talk about multiple times in the course. And logistic regression scores high on interpretability because we can really see what it's doing under the hood. Okay, so yeah, logistic regression is super popular. It's fast, it's interpretable. It's a really good thing to have in your toolbox. And we will be using it a whole lot in this course, as you will see, as a sort of first pass at working on a problem. Okay, let me take a look in the chat box here. What happens if the review is, I see. So yeah, that when you add up all the coefficients, it then passes that through a function that maps it to be between 0 and 1. I just skipped over that, but I really should add it, so please remind me on Piazza. I think I tried to avoid math in this course, but I think I maybe took it too far in that case. And I can show you that function. Does it count the word twice? Not in this case, because we set binary equals true when we made the CountVectorizer. But if we didn't do that, then it would count the fact that the word appeared multiple times. Can logistic regression be used on the Spotify dataset? Absolutely. Logistic regression doesn't have to, that's an awesome question. You don't have to use logistic regression only for text. Any tabular data set where you have features, you can use logistic regression. And what happens if you use logistic regression on the Spotify data set is you'll have a coefficient corresponding to danceability and a coefficient corresponding to loudness and a coefficient corresponding to all those other things. And it'll be the interpretation is slightly more complicated, and we'll talk about it. But yeah, you can totally use logistic regression on the Spotify data set. Is the text graph? Oh yeah. Sorry, no. Yeah, I probably changed a random seed and came up with a different example. Yeah. Okay. Is logistic regression only used for binary output? Excellent question. No, it is only used for classification, but there is a way of using it for more than 2 categories in the output, like cat, dog, mouse, positive, negative, neutral, and we will see that later in the course. Okay, we're almost there. So going back to the question in the chat of can we use logistic regression on the Spotify data set? Absolutely, we can use it on any data set. So I'm going to use it on the Cilantro data set here. So again, I create my logistic regression. I fit it on X and Y trained from the Cilantro data set. And when I plot classifier, what we have here is basically a slice. And so the interpretation of logistic regression when you have continuous features. So remember in the first class, I talked about how features could be continuous or discrete. And so in the word count case, those features were just 0 or 1. Is the word present or not? In the Cilantro case, the features are, they're continuous numbers, right? So 185, whatever. And so if we want to look at it, this is what logistic regression is doing. And that's basically what it does in general, is it slices the space. And we can visualize this in 2D. It's a bit harder to visualize in 3 or especially 4 or 5 or more dimensions. But that's what the visual interpretation of logistic regression when you have continuous features. It can also be used when you have a mix of continuous and discrete features. And we'll be talking plenty more about that in 2 or 3 lectures from now. So yeah, there's still the coefficients. The interpretation is just a little more complicated. So it's this is the coefficient for meat, and so it's saying if you eat more meat, then you're probably not going to like cilantro. That's what negative means. And this is positive. That means if you think you'll get a higher grade, you probably are going to like cilantro more. And we can see that here, meat is the x-axis. So as we move this way and eat more meat, we start going from yes to no. And as we start going to higher grade, we start going from no to yes. So that corresponds to the meat coefficient being negative and the grade coefficient being positive. Okay, so plot classifier function can also show the probabilities. And so you can actually make this picture with the output of predict proba instead of the output of predict. And this is really cool, I think, because now you can see that near the boundary, the probability is basically, the probability score, I want to call it the probability score, is close to 0.5. That's like, I'm unsure, do you like cilantro or do you not like cilantro? And as you get farther away from the boundary, the scores get closer to, 1. It's very skewed towards liking cilantro, or 0, very skewed towards not liking cilantro. And the last thing I want to talk about today is an important hyperparameter for logistic regression, which is C. And so C is a huge topic in CPSC 340, and we spend many a class talking about C. But in this course, all we're going to say about it is that it is a model complexity hyperparameter. Just like max depth of a decision tree, if you had a bigger value, that means more complicated models, more overfitting. Smaller value means less complicated models, less overfitting. It's the same thing here with C. So larger C means more complicated model, more overfitting, and smaller C means less complicated model, less overfitting. So let me actually first show you this. Okay, so here I'm going back to the IMDb data set, and I'm fitting it with default C, which is C equals 1. And then I'm fitting it with a large value of C, which I just said should give you a more complicated model. And what you see here is you get a perfect training accuracy, but more overfitting, just like we talked about with max depth. And if I have a smaller value of C, then it's the other way around. And I get a worse training score, but less overfitting. And in this case, it seems to be better overall. And so I can make those same plots that we made before. Again, I'm not doing cross-validation for today, even though in general, I want you to do cross-validation all the time. That will all become clear next class. There's just like this bottleneck of things we need to teach in the beginning of the course. And it's hard to pick them in the right order, and I'm still kind of trying to figure that out. But we get the same kind of plot. So here we have the test score. I should really, let me just add this in. I really want to be showing you the train and test at the same time. I don't remember why I didn't do that. Okay, so the orange thing is the training score. It just gets to 100% as you make the model more complex. We saw that before with decision trees. The test thing here, it's the same kind of thing. So over here, the model's too simple. It's underfitting. There's kind of this sweet spot here where the test score gets a bit better, and then it gets bad again. So it's probably unnecessary to make this plot so far off to the right. Yeah, so we get this again. If I had to pick C, I would probably pick it around here, like around 0.01 or something, because that's giving me the best. Again, should normally be cross-validation score, and next class will make it cross-validation score, but I'm just using test for the moment. Okay. Yes, so there's true-false questions we can do on Piazza, and hopefully more of you can participate in between this class and next class next time. So let's just finish off with a final Q&A. So just give me a minute to scroll up. Cilantro and red meat, okay. I would expect more positive correlation between liking cilantro and liking meat. Yeah, I mean, this data set's super small, and so it's not very reliable, but there seems to be a kind of mild negative correlation in that according to you all. What does a more complicated a logistic regression model actually mean? Yeah, excellent question. It's hard to answer that. Okay, basically what it more complicated means is it means it's allowing the coefficients to be bigger. And when the coefficients are bigger, that causes it to overfit more, because when it just sees a single thing, it's like, oh, that thing, that's like the most positive word ever, and jumps to a conclusion. And so that does well in the training set because it makes the coefficients big, and it jumps to the conclusions where it knows the answer. But on the test set, you have these big coefficients, and it kind of reads too much into seeing a single word or a single feature. And of course, there's way more details in 340, but that's kind of a high-level answer for now. So yeah, we're really not going to get into what C represents, other than, like I just said, bigger C allows the coefficients to be bigger, but more importantly for us in this course is it skews things towards higher training accuracy, more overfitting, and it's really just one of many hyperparameters that we're going to be seeing all throughout the course with all different models. How can we have a negative C? We can't have a negative C. That's not allowed. So C does not represent cilantro. It is a hyperparameter of logistic regression, just like max depth is a hyperparameter of decision tree. With max depth, I could really tell you what it meant. Like, we drew the trees, we looked at the picture, we said how deep is the tree. With C, we don't have time in this course to really go into what it does. And yeah, it is generally a challenge to draw the line between 330 and 340, but I really want this course to provide value for people who take both courses, and I think it does. I hope it does. But that means I may have to leave you slightly unsatisfied sometimes to save time. But maybe, on the flip side, that could leave you curious to take another course. Feel free to follow up more on Piazza about this as well. Can you explain how we choose the best value of the hyperparameter like max depth or C? So that is, next class is literally, the title is hyperparameter tuning. So all of next class is basically about that question. How do we pick the best value of C? And it's going to be awesome. It's a topic close to my heart. We are out of time, so let's wrap it up here. Nice to see all of you, and I'll see you on Thursday.